Reinforcement learning got very good at formal mathematics and software engineering, and it's still bad at driving a browser. That ordering is backwards, because computer use is more verifiable, not less. So verifiability isn't the variable. Something else is doing the work, and once you find it, 15 years of DevOps maturity starts to look different.
Yeah, I mean, it is genuinely one of the most counterintuitive puzzles in the entire field right now.
Right. I mean, welcome to the deep dive, everyone. Today, we're looking at this really fascinating stack of research papers on reinforcement learning, and we're combining that with some recent cybersecurity threat reports to figure out what that hidden variable actually is. Because, well, our mission today is to understand this massive discrepancy in AI capabilities.
Yeah, because if we misdiagnose why AI succeeds or, fails in certain environments,
Yeah,
our entire enterprise security model essentially just, well, it breaks.
it totally breaks. Yeah.
We really are at a critical juncture with this. We're building all our defensive perimeters based on assumptions about what automated adversaries can and cannot do.
Right.
And if those assumptions are rooted in the wrong fundamental variable, we are quite literally fortifying the wrong walls while leaving the vault wide open.
Yeah, which is terrifying. So, okay, let's unpack this core puzzle first. Because, on the surface, the current state of AI capabilities makes absolutely no sense.
It really doesn't.
Like, if we look at the research papers in our stack today, if I ask a cutting-edge reinforcement learning agent to prove a highly complex, graduate-level theorem in formal mathematics.
Using something like lean or alpha geometry.
Exactly. Lean or alpha geometry. It can do it. It's world-class. It navigates these incredibly abstract, high-dimensional logic spaces.
Flawlessly.
But if I ask that same state-of-the-art agent to navigate a standard web browser and just, successfully submit a checkout form on a basic e-commerce site, it completely falls apart.
It is a spectacular failure mode, too.
Yeah, it really is. The research shows these agents they get stuck in infinite loops. They hallucinate button clicks. They try to interact with elements on the page that don't even exist.
Yeah.
They freeze up because a pop-up appeared. And, the prevailing assumption in the tech industry has always been that AI struggles with tasks that are hard to verify.
Right.
But checking if a web form went through, that is incredibly easy to verify mechanically.
Yeah.
Did the order confirmation URL load? Yes or no? Did the database increment? Yes or no? It's perfectly verifiable. So I guess the question is, why is AI mastering abstract, high-level math, but stalling out on a basic web task that, any teenager can do with their eyes half closed?
Well, the key here is that we have been conflating verifiability with learnability.
Okay, wait, what's the difference?
So verifiability just means we can check the final answer.
Right.
We can grade the test. But for an AI to learn how to achieve that final answer.
Especially through trial and error, right?
Yeah.
Reinforcement learning.
Right. Especially through reinforcement learning. It needs an environment that actually supports the learning process itself.
Yeah.
So the hidden variable that is actually dictating AI capability isn't verifiability.
Okay.
It's a property called grindability.
Grindability, okay. Like grinding levels in a video game.
Actually, yeah, the gaming analogy is a really great starting point for this. But let's dive into the mechanics of what that actually means mathematically.
Yeah, let's do it.
Formally, grindability is the degree to which an environment's return, so meaning the final reward or outcome, is a deterministic function of the agent's action sequence.
Okay, deterministic function. So meaning if I do the exact same actions, I get the exact same result every time.
Precisely. And to truly understand why this matters, we have to look under the hood at how these systems learn. We're talking specifically about policy gradient methods in reinforcement learning here.
Right. So we are basically talking about trial and error on a massive scale. The AI tries a sequence of actions, gets a score, and then updates its internal weights, its policy, I guess, to favor the actions that led to a higher score.
That is the basic loop.
Yeah.
But the challenge is a concept called credit assignment.
Credit assignment.
Right. So when an AI takes 1,000 actions and then gets a final score, how does it know which specific action was the one that helped and which one hurt?
Oh, like if I press up, down, left, right, jump, and then I win, which of those actually mattered?
Exactly. Was it the jump? Was it the left? To figure that out, policy gradient algorithms require a massive amount of samples. Millions, sometimes billions of attempts.
Wow.
And to learn anything from those millions of attempts, they rely on variance. They're essentially looking for the difference in outcomes based on the difference in actions.
Okay, so variance is basically the teacher.
Yes.
If I do X and get a bad score, and then I do Y and get a good score, the variance in my score tells me Y is better than X.
Only if the environment is stable enough to guarantee that your action was the only thing that changed. And this is where the theory gets crucial, because there are actually 4 different sources of variance in any given environment.
4 sources, okay.
And if the AI is trying to learn, 3 of those sources are basically just static noise.
They just confuse it.
Right. They completely ruin the learning process. Only one source is the actual signal it needs.
So let's break those 4 down, because I want to map this directly to why the web browser fails so badly.
Yeah, let's do it.
Yeah.
So source number 1 is reward stochasticity.
Okay. Reward stochasticity.
Right. This means the grading system itself is random or noisy. Imagine taking a math test where the teacher rolls a dice to decide if your correct answer gets a point.
Oh, that sounds incredibly frustrating.
Right. You can't learn in that environment because doing the right thing doesn't reliably give you a reward.
Yeah.
So you eliminate this first source of noise by having a deterministic verifier.
Mechanical oracle.
Exactly. A mechanical oracle that always gives the exact same score for the exact same outcome.
Okay, so that is verifiability. We eliminated the noisy teacher. If I submit the checkout form successfully, I always get a 1. If I fail, I always get a 0. That's source 1 down. What's source 2?
So source number 2 is initial state variance.
Initial state.
Yeah. This means every time the agent attempts the task, the starting conditions are slightly different.
Give me an example of that.
Well, if you are trying to learn how to shoot a basketball, but every time you try, someone moves the hoop to a different height or distance,
Oh, I see.
they're going to struggle to build muscle memory. Your baseline is always shifting.
Right. You can't isolate what you're doing wrong if the hoop keeps moving.
Exactly. So to remove this source of noise, you need identical resets. Every single new attempt must start from the exact same baseline condition.
A clean slate every time.
Correct. So that's 2. Now, source number 3 is transition stochasticity.
Transition stochasticity. Okay.
This is when the rules or the physics of the environment change while you are in the middle of interacting with it.
Oh, okay.
In our basketball analogy, this would be like a sudden gust of wind blowing the ball off course while it's in the air, or the floor suddenly becoming slippery right as you jump.
Jeez. Yeah, that would completely mess you up.
Right. You take an action, but the environment's response to that action is unpredictable.
Yeah.
So you remove this by having deterministic dynamics.
So the physics of the world need to be completely stable and predictable.
Yes.
Okay, let me think about this. We want to remove the noisy reward. We want to remove the shifting starting line. And we want to remove the changing physics.
Right.
If we successfully eliminate all 3 of those, then the only variable left that could possibly change the outcome is the AI itself.
You've got it. The 4th source of variance is the policy's own action choices, what the AI agent actually decided to do.
Right.
And this is the critical part. This is the actual signal. This is the only variance you want the system to have.
Because if the reward is perfectly consistent and the starting state is always identical and the environment's physics never drift, then any difference in the final score is 100% mathematically attributable to the sequence of buttons the agent pressed.
That is precisely how credit assignment becomes tractable for the algorithm. The delta in the outcome is entirely caused by the delta in the agent's actions. The difference is the causal factor.
Wow.
So a perfectly grindable environment is one where those first 3 sources of variance have been completely eliminated.
That maps so perfectly back to the video game analogy.
Doesn't it?
Yeah. Like, let's look at formal mathematics, proving those theorems in a system like Lean. It's basically like playing a single-player video game on an emulator where you have a quick save feature.
All right.
If I want to beat a difficult boss, I can quick save right before the fight. That gives me an identical reset.
Which eliminates source number 2.
Exactly.
Yeah.
And the code of the game doesn't change. The boss's hitboxes are always the exact same pixels. That's deterministic dynamics.
The source number 3 is eliminated.
Right. And the game's code perfectly calculates my health and the boss's health. Source 1, perfect verifiability, is eliminated.
Exactly.
I can grind that boss fight 10,000 times in a row under the exact same sterile conditions until I execute the mathematically perfect sequence of button presses.
And what's fascinating here is that formal math gives the reinforcement learning algorithm all 3 of those variance removers for free.
Right, because math is just math.
Exactly. A mathematical theorem provides a perfect identical reset. The axioms of mathematics do not experience drift overnight.
Right.
And the proof checker is a flawless deterministic oracle. The environment is perfectly grindable, which is why the AI achieves world-class performance.
But driving a live web browser,
Oh.
that is not a single-player emulator. That is an online multiplayer game on a shaky internet connection. You do not get a quick save.
Not at all. I mean, walk through what happens when an AI tries to interact with a live web page.
Well, let's say it tries to fill out the form and fails, so it hits refresh to try again, but a live web page doesn't give you an identical reset.
No.
When you refresh, maybe there's a new targeted ad at the top of the page.
Yep.
Maybe the company pushed an A/B test and the submit button moved 3 pixels to the left.
Exactly.
Maybe the DOM structure, like the underlying code of the page, loaded in a slightly different order, so the initial state variance is just massive.
And what about the transitions?
The transitions are incredibly stochastic. Like, the AI clicks a drop-down menu. On attempt number 1, the network latency is low, and the menu opens in 50 milliseconds.
Right.
On attempt number 2, the server is under heavy load, and it takes 2 seconds to open. The AI, expecting the menu to be there instantly, fires its next click, misses the menu, and clicks a random banner ad instead.
And then what happens?
A pop-up appears asking for a newsletter sign-up. The entire physics of the environment just shifted under its feet.
Yes. And this is the crux of the failure. Computer use, navigating a live browser, only gets the first variance remover for free. Verifiability.
Right.
We can easily verify if the checkout form was submitted and the database incremented, but the environment fails catastrophically on initial state stability and transition stability.
So verifiability is necessary, but the research clearly shows it is not sufficient.
Exactly.
So when the AI agent gets confused and, hallucinates a button click, it's not because it's stupid.
Right.
It's because the credit assignment problem is mathematically impossible in that environment.
Precisely.
It tries a sequence of actions and fails. But because of the shifting ads, the latency, the pop-ups, it doesn't know why it failed. Did it click the wrong button, or did the page just load too slowly that time? The variance is mostly noise, not signal.
Exactly. And reinforcement learning algorithms require a sample size that scales with the variance of the environment.
Right.
So in a non-grindable environment like the live web, that variance just explodes. To find the true signal amidst all that noise, the sample complexity exceeds what adversarial infrastructure and current compute budgets can handle.
Wow.
People have been assuming for years that AI couldn't surf the web effectively because of sophisticated bot detection like CAPI-TCHAs or, behavioral analysis.
Yeah, that's what I always thought.
But bot detection isn't the fundamental barrier. The fundamental barrier is that the live web is a terrible environment for credit assignment.
Okay, so we've identified the hidden variable. Grindability is the secret sauce. If an environment is highly grindable, an AI can master it rapidly. If it's noisy and stateful, the AI stalls. But how do we actually measure this? Because right now, grindability sounds a bit like a theoretical concept. Is there a concrete mathematical way to pin this down across different systems?
There is. And this brings us to a piece of academic pedantry that absolutely matters in the real world.
Okay, academic pedantry. Let's hear it.
Grindability isn't just an inherent aura that floats around a system. It is a mathematical metric known as a variance decomposition ratio.
Variance decomposition ratio.
Right. In very simple terms, it is the fraction of the total return variance that is attributable to those first 3 sources. The noise versus the fourth source, which is the agent's policy.
Okay,
But here is the massive trap that research labs and security teams fall into. That ratio changes depending on the optimizer you are using.
What?
Yeah. If you don't declare a reference policy class, a specific estimator, and a time horizon, the entire construct dies.
Whoa. Okay, variance decomposition ratio, reference policy class, advantage estimators, time horizons, timeout. That is a heavy jargon drop.
Fair enough, yeah.
Can we get an I'm 5 foot moment here? Because I want to make sure I'm fully grasping why this measurement changes.
Absolutely. Let's use a sports analogy.
Good.
Imagine a track and field coach trying to figure out if a new type of running shoe, which represents the environment, actually makes athletes faster.
Okay, shoes are the environment.
The grindability is essentially how clearly the coach can see the impact of the shoes amidst all other noise, like the weather or the athlete's mood or whatever.
Right. The signal versus the noise.
Exactly. But here's the catch. How the coach grades the performance completely changes the results.
What do you mean by how they grade? A stopwatch is a stopwatch, right?
Well, this is the advantage estimator. If the coach grades every run against an absolute world record time, the variance looks one way. Most people will just look terrible compared to the world record.
Okay.
But what if the coach grades on a curve? What if they compare today's run only to that specific athlete's rolling average from the last week?
Oh. Suddenly the score for the exact same physical run changes.
Yes. The mathematical variance shifts entirely based on the baseline the coach chose to use.
Ah, okay. So the reference policy class is basically deciding which baseline of student or athlete we are comparing against. Are we comparing against a novice or an expert?
Exactly. And the time horizon is whether the coach is looking at the improvement over a single 100-meter dash or over an entire decathlon season.
I see.
If you don't declare exactly how you're estimating the advantage and over what time frame, your numbers mean absolutely nothing. If one AI lab measures the grindability of a web testing suite using a specific advantage estimator that grades on a short-term curve, and another lab measures the exact same web suite using a different baseline that looks at long-term absolute scores.
They're going to get completely different numbers.
Completely different grindability numbers for the exact same software.
So grindability isn't an absolute universal property of the environment itself, like the boiling point of water or something.
No, it is a scale-free ratio, and it is entirely estimator relative. You must declare your reference estimator.
Right.
If you don't state what mathematical lens you use to measure the variance, the numbers become incomparable between organizations, and the whole concept falls apart as a useful metric.
Got it. Okay, so we have this metric. It tells us how efficiently an automated agent can learn and optimize within a given environment.
Yes.
And if the environment gives identical resets, deterministic physics, and a clean pass-fail reward, it is highly grindable. The AI will optimize against it very, very fast.
Which brings us to the core security implication of this entire deep dive.
Okay.
Because determinism, replayability, cheap resets, and a mechanical success oracle, those are not Defender-specific affordances.
Wait, what do you mean?
They are properties of the environment, and they are available to whoever is optimizing in that environment.
Hold on. Identical resets, deterministic physics, pass-fail oracle. We aren't just talking about abstract math theorems or video game emulators anymore, are we?
No, we are not.
You just described my engineering team's Monday morning.
Yep.
You just described a modern CI/CD pipeline.
Exactly. Let's look at the list of practices from the security reports in our source stack. Look at what the tech industry has spent the last 15 years perfecting in the name of DevOps maturity.
Okay, I have the list right here. Let me just read this slowly. Hermetic CI.
Yeah.
Reproducible builds,
Uh-huh.
containerized staging environments that faithfully mirror production,
Right.
deterministic test harnesses, infrastructure as code, seeded fuzzing Horpra.
Think about those practices through the lens of the variant sources we just discussed. What is that list, really? It is a list of tools explicitly designed, at massive expense, to systematically eliminate the first three sources of variance from our corporate networks.
We built hermetic CI and reproducible builds specifically to eliminate initial state variance. Like, we wanted identical resets so our developers wouldn't have those "it works on my machine" problems.
Exactly.
And we built deterministic test harnesses to eliminate transition stochasticity. We wanted the rules of the code to be perfectly stable so tests wouldn't flake out.
Right.
We built all of these things to make our own systems perfectly testable.
And here is where it gets really uncomfortable. We spent 15 years making our systems easier to optimize against. And the optimizer has arrived.
We didn't just build great testing environments for our developers. We systematically built the ultimate, mathematically perfect AI training grounds for our adversaries.
That is the uncomfortable truth. By making our systems perfectly testable, we made them perfectly attackable.
Oh my gosh.
Every single DevOps practice that raises grindability for your quality assurance team also hands an automated adversary a replayable, deterministic, cheap reset sandbox with a mechanical success oracle.
Okay, let's actually visualize how this works mechanically, because I really want the listener to feel the impact of this.
Sure.
Let's say I'm an automated reinforcement learning agent, and I've managed to get access to a company's continuous integration pipeline. What does my attack actually look like compared to attacking, say, a messy live web server?
Well, if you attack a live web server on the internet with a SQL injection, the server might hang.
Right.
It might drop the connection. A web application firewall might temporarily block your IP or rate limit you. The response time varies. You are dealing with massive transition stochasticity and initial state variance.
It's noisy.
Very noisy. Your AI struggles to learn from the noise. It can't assign credit to its actions.
But inside the CI pipeline.
Inside the CI pipeline, you have infrastructure as code. You can spin up a pristine, containerized clone of the production database in milliseconds. You fire your experimental SQL injection payload. The deterministic test harness catches it, blocks it, and instantly returns a beautifully formatted, highly specific error code telling you exactly which syntax failed.
Oh, wow. So that is your mechanical success oracle.
Exactly.
So the AI parses that exact error code, updates its policy, and then because it has reproducible builds, it just throws away the tainted container, spins up a mathematically identical fresh container, and tries the new payload.
In milliseconds.
Yeah.
Over and over and over again. Thousands of times a minute.
Jeez.
No rate limits, no messy network latency, no shifting variables. The environment provides perfect credit assignment signal.
So the AI can just grind against your internal APIs.
It can find every edge case, race condition, and logic flaw at light speed because the delta in the outcome is 100% attributable to the delta in its payload.
That is terrifying. But let me play devil's advocate here for a second.
Please do.
Because my inner CISO is screaming right now. I hear what you're saying about CI being highly grindable, but I mean, it's behind my firewall. My team built it. We control the specification. We have comprehensive logging. We can see everything happening in there. Doesn't the home field advantage count for anything? Like, the attacker still has to actually break into my network to access this pristine training ground.
And that is a very sharp pushback. It's the exact right question to ask.
Right.
Because if we claimed that high grindability was an unconditional, universal advantage for the attacker, the entire argument would fall apart immediately.
Exactly.
As you said, the defender controls the environment. We have to bound this claim to make it scientifically survivable.
Okay, so what's the bound?
The rule of grindability, the fact that testability equals attackability, is symmetric, conditional, unequivalent access.
Conditional on equivalent access, meaning the attacker still has to get inside the building before they can use the gym.
Yes. Grindability is not an argument about attack surface.
Okay, how are we defining attack surface here?
Attack surface is about how easy it is to get in. How many open ports do you have exposed to the public internet? How weak is your authentication? Are your employees falling for phishing? That is your attack surface.
Got it.
Grindability, on the other hand, is an argument about attack efficiency.
Yeah.
It dictates how fast and how comprehensively an automated attacker can exploit you once they are inside.
Okay, let's run this through what the sources call the air gap test.
Good idea.
Let's say I have a fully internal, air-gapped, perfectly hardened, continuous integration environment. There is no inbound network path from the internet whatsoever. My attack surface is effectively zero.
Your attack surface is zero.
Right.
But if an attacker does breach that perimeter, perhaps through a compromised insider or, more commonly a poisoned open source supply chain dependency that gets pulled into the build process.
Yeah, that happens a lot.
If they get in, that perfectly hardened deterministic CI environment is maximally grindable.
Because once they are in, my home field advantage doesn't degrade their AI.
Exactly. Nothing about your hermetic determinism reduces the value of the environment to the adversary who is now sitting inside it.
It's almost like it helps them.
It does. It is the exact opposite of degrading their AI. Because you made it highly reproducible and heavily instrumented for your own developers, you have provided the attacker with the perfect laboratory.
Oh my gosh.
They don't need to guess how your production environment is configured. The infrastructure as code files tell them explicitly. They don't need to worry about noisy network traffic. The test harnesses give them clean signal.
Wow. So by adopting 15 years of DevOps best practices, we haven't necessarily increased our attack surface,
Right.
but we have massively increased our attack efficiency inside the perimeter for whoever manages to get there.
Precisely.
And that is a totally different metric. I don't think I've ever seen a risk register that tracks attack efficiency as a separate variable from attack surface. We treat them as the same thing, but they aren't.
No, they really aren't. And this brings us to a crucial status check on this entire theory.
Okay, let's do the status check.
If this hypothesis holds true, if grindability truly governs automated search efficiency, then we can make a very specific prediction about what we should see in the real world.
Which is?
Attacker behavior should heavily concentrate on highly grindable targets.
Right. If attackers are rational, we should see automated exploit tooling going after package ecosystems, CI systems, API surfaces with free tiers, anything where they can easily reset the state and get a clean pass-fail response.
Yes.
They should naturally avoid bespoke, weird, non-reproducible legacy enterprise systems where the physics of the environment are muddy and the AI can't learn.
That is the prediction. But if a security researcher sets out to prove this, there is a massive statistical trap waiting for them.
A trap.
It is called the detection bias confound, and it is vital We understand it before we look at the data.
Yeah.
Let's say a researcher says, I'm going to look at public incident data and breach reports in the last 5 years to prove that attackers love grindable environments.
Okay, sounds logical.
If they do that, they are going to get completely corrupted data.
Wait, why is the incident data corrupted?
Let's introduce a metaphor here and make this clear. Imagine a hospital that just bought a state-of-the-art X-ray machine.
Okay.
Suddenly, they are diagnosing 3 times as many broken bones as they were last year. Does that mean the city is suddenly experiencing a massive wave of bone fractures?
No, it just means they finally have the tool to actually see the fractures that were already happening.
Precisely. Grindable environments like hermetic CI pipelines and reproducible builds are highly deterministic and heavily instrumented by design.
Right.
Because the physics are so stable, any anomaly stands out like a sore thumb. They are incredibly easy for defenders to monitor. These environments are the X-ray machine.
Ah, I see. So of course we catch more attacks in highly grindable environments, not necessarily because attackers target them more, but because our visibility in those environments is so much better.
Exactly.
If we use incident reports to prove our theory, we aren't measuring attacker preference at all. We're just measuring our own observability. We'd be correlating grindability with our own ability to detect things.
It is a classic detection bias trap. If we rely on what we catch, we will falsely confirm our hypothesis.
Wow, that is such a subtle but important distinction. So how do we actually measure this? How do we prove the prediction without falling into the detection bias trap?
The true measure is something economists call revealed preference.
Revealed preference.
Yes. Instead of counting the attacks we happen to catch on our own networks, we need to look at the open source and dark web repositories. We need to count the publicly available automated attacker tools designed for these specific classes of environments.
Oh, I like that. We look at what the tool builders are actually spending their time creating.
Exactly. Attackers, just like commercial developers, build automation where automation works. It takes time and money to build an automated AI exploit agent.
Right.
If we see a massive proliferation of automated exploit tooling built specifically to attack CI/CD pipelines, package managers, and deterministic APIs, and conversely, we see very little automated tooling built for stateful, clunky, undocumented legacy systems. That validates the theory.
We look at the GitHub repos for offensive security tools, not just the defensive incident reports.
Yes, but I must be explicit here, as this is a crucial distinction for the rigorous science of this deep dive.
Okay.
This is currently a prediction with a proposed measurement protocol. It is not yet a confirmed experimental result. The data gathering on revealed preference is still ongoing.
Good to know. Okay, this brings us to the Monday morning problem.
Right.
What does this all mean for the listener? I mean, if I'm an engineering manager, a VP of platform, or a CSISO listening to this, my heart rate is probably a little elevated right now.
Understandably so.
I have spent millions of dollars in years of political capital getting my stubborn organization to finally adopt reproducible builds and hermetic CI. I fought tooth and nail for that DevOps maturity.
I know a lot of people in that exact position.
I understand the tension here. The business demands developer velocity, and developer velocity demands grindability. I am not going to throw away my CI pipelines, burn down the Kubernetes clusters, and go back to developers manually shipping code from their laptops over FTP just to confuse an AI attacker.
No, nor should you. That would be catastrophic for the business.
So how do we practically live with this reality? How do we secure systems that are inherently designed to be optimally attackable? Let's walk through some concrete, escalating steps the listener can take, starting with lowest cost and moving up.
Okay, step 1, the lowest cost action you can take on Monday morning is to simply score your own environments.
Score them how?
You don't need a complex mathematical variance estimator or a data science degree to start. You just need to ask 4 simple questions about any environment your team manages.
Okay, let me write these down. What are the 4 questions?
1 is the reset identical. Can you spin up a fresh state instantly?
Okay.
2, are the transitions deterministic? Are the rules of the system stable? 3, is there a mechanical success oracle? Does the system give a clear, pass-fail, or explicit error code?
Yep.
And 4, is reproduction cheap? Can an agent loop this process thousands of times without massive resource strain?
So I walk through my architecture, and if a system like my CI pipeline or a staging API scores a 4 out of 4 on those questions, I know I have built a maximally efficient search environment for an attacker. It is highly grindable.
Exactly. You map the terrain, you figure out where your risk actually lives.
Okay, that's step one. What's step two?
Step two, which involves medium cost and some organizational friction, is to separate these concepts in your risk register. You need two distinct columns or budgets: an attack surface budget and an attack efficiency budget.
This requires changing how governance thinks about risk.
Yes, entirely. You must document your attack surface work distinctly from your attack efficiency work. When your platform engineering team says, hey, we want to implement fully determined at a governance level, that raising that testability inherently raises adversarial efficiency once the perimeter is breached.
So you aren't saying stop doing it. You're just saying account for the cost. Put it on the ledger. Like if we do this, developer velocity goes up by 20%, but our internal attack efficiency for an adversary also goes to maximum?
Right. It makes the trade-off visible. And that visibility leads directly to step three, the highest cost action, but the most vital for your security posture.
Okay, lay it on me.
Put the heaviest access barriers where the grindability is highest.
Because the symmetry is conditional on access?
Exactly. Since we established earlier that the attacker only gets the advantage of grindability if they have access, you have to relentlessly lock down the environments that scored a 4 out of 4 on your Monday morning test.
Which, ironically, is usually the CI system. And this is where the industry has a massive blind spot, doesn't it?
It's huge.
In most organizations, the CI pipeline has some of the weakest access controls. It's treated as a friendly internal dev tool, like every junior developer has access to it.
But it has privileged reach straight into the production environment.
Right. We have built the ultimate AI training ground, the perfect sandbox, and we are leaving it virtually unguarded.
It is the most valuable real estate on the network for an automated adversary, and we treat it like a communal bulletin board.
Wow.
If an environment is highly grindable, it must be gated with the strongest authentication, the tightest anomaly detection, and the most rigorous zero-trust policies you can muster.
Next time, we are going to look at what happens when the reward function itself contains a term that correlates with resources on the other side of your isolation boundary. It's going to completely reframe how we think about container security.
It really is.
But for now, I just want listeners to think back to that X-ray machine we talked about during the detection bias segment. We thought the reason AI struggled with certain tasks was because they were hard to verify. But it turns out the murky, messy, unpredictable nature of the real world, the shifting ads, the network latency, the unpredictable physics was actually the only thing protecting us from automated learning agents.
Exactly.
And in our quest to clean up that mess inside our corporate networks, to make our systems perfectly visible, perfectly reproducible, perfectly clean, we didn't just build a better X-ray for our developers, we built the exact lens our adversaries needed to see right through us.